Hi, my name is Manish Gupta, and in this video, I'm going to talk about Decaf, which is Deep Extreme Classification with Label Features. So let's get started. Okay. So broadly, how does Decaf work? Well, please go over my previous video if you have not done that. So because Decaf is a deep XML algorithm. So in the previous video, I talked about deep XML and then an algorithm as stack based on that. Decaf is also a deep XML algorithm. Okay, so it follows the deep XML pipeline. Decaf has three particular components: a text embedding block, one versus all classifiers per label, and then a shortlister to get high recall label shortlist for data points. Okay, so essentially, Decaf is also meant for text-based extreme classification. So, for example, if you have a document, you basically can embed the document. In this particular case, a Wikipedia document like Taj Mahal, right? There is an embedding block, and we'll talk about this embedding block in more detail in the remaining part of the video. But much of it is very similar to what we have already discussed in the deep XML kind of video. Okay. Um, and then followed by a ReLU layer. So that basically gives you your document embedding, the text embedding block. Yes, that's that. Now, if you basically in extreme classification, the number of labels are too many. So if you were to essentially perform evaluation with respect to all the labels, then that would be too much. That would be very, very computationally intensive. Therefore, what Decaf has is this shortlister block. So this is a shortlister block. Given a very large label set, it basically tries to shortlist a few labels that make sense. So for example, this set and this set. Now out of these, notice that these four labels L1, L13, L11, and L4 are valid labels. They're relevant labels, but the others are also there because, well, you have to select some sets as part of shortlister. Okay. So that's the shortlister. And then the third component is this ranker. So after the shortlist has been done and you have like 6 different labels, you essentially try to use these one versus all per classifiers per label and then rank, let's say W4 up, higher up, W11 next, W9 next, W1, W13 and W6. So if one were to just take top 5, you would have a precision of 4 on 5 because you would have selected the 4 good ones except for one W9, which is incorrect. Okay. So rather, label 9, which is incorrect. So Ws are essentially, yes, the classifiers, but the labels are L4, L11, L9, and so on. So that's that. Now, broadly, that is how Decaf works, but that's not enough. So let's basically therefore go into details and understand more closely how Decaf works. OK. So Decaf basically is for text-based extreme classification. So therefore, as we discussed, it has a text embedding block. And here are details of the text embedding block. OK. Some notations first. So L is the number of labels, V is the vocabulary size. So there is text associated with both the document input and also with the labels. Okay, and both kinds of text are going to be used here. So V is the vocabulary size, N is the number of training points, and YI basically tells you whether a particular training point is relevant for a particular data point or not. Okay, so that's that. Now. There are this text embedding block, as you see. So text embedding block. So essentially the way it embeds is as follows. You take a vector. So it takes an input vector V. So you take the vector V, you do a ReLU on top of it, and then you essentially have you see this R, which is basically a D-dimensional D cross D matrix, D cross D matrix. You take the vector V, apply ReLU, apply D cross D matrix, and then you apply something called the combiner block, and that gives you your overall embedding. Okay. Now, the combiner block, of course, is combining V along with this processed stuff. Okay. And then how does it combine? Well, it combines in this way. So the combiner block actually is this. Okay. So let's go over it one by one. So you take V, you basically take you apply ReLU to V, and then you also multiply it with R. And then you combine, this R into ReLU of V and then the V itself. OK, so that is how the combination is happening. The way you combine is using the combiner block. The combiner block basically has two things. One, so basically the combiner block essentially takes two things, right? U and V. So in our case, it is basically V and R into ReLU of V. OK, so what does it do with U and V? Well, it basically also has these free parameters alpha and beta. So these are parameters to be trained, right? So you apply sigma of alpha. So you apply the sigmoid on top of alpha, you apply sigmoid on top of beta, and then you multiply element-wise multiply with u and v, and then you overall add it. Okay, element-wise addition, and thereby giving you a vector in the end. Okay. So there are two basic blocks in Decaf, the text embedding block and the combination block. Now, more details. Let's look at more details. So for each label, you basically have labeled text. So for example, if the problem is about Wikipedia to category mapping, well, the categories also have some text. They have some names. Okay, so we represent the label text as ZL. OK, so essentially for any label, the label text is going to be represented as ZL, and it also has words belonging to the vocabulary. OK. Now, when you have any piece of text R, now it could be any piece of text R. OK, so the way you basically get the overall embedding is basically you multiply this R with the embedding matrix E, not shown anywhere here. OK, it's an embedding matrix E, so as to get R hat not. OK, this is randomly initialized, but you could also initialize it using fast text or some such thing. So Aztec basically had it initialized using fast text, but Decaf basically just randomly initializes E. Now you take R naught hat and essentially the embedding block, the way it is going to give you output is basically by taking R hat not, so basically here this V is essentially nothing but R hat 0 or R hat not. OK, and then this is R into capital R into ReLU of R hat not. And then the combination is also happening sigmoid of alpha and beta element-wise multiply, and then you do element-wise addition. OK, so that's that. So that's how the embedding block essentially consumes inputs from the combination block so as to finally give you a representation. Now, they use this embedding block to embed both the documents as well as the labels. So let's see how that's done. OK, so for the documents, it's sort of pretty simple. You take a document xi, you pass it through the embedding block. So if the document is the Tallis Scholar Sings Josquin, right? So you don't consider the stop words, but you take all of these 4 words, you essentially just do a bag of words representation for them, and that's what you call as xi. OK, you take that xi and pass it through ed. And what is ed? By the way, ed is this entire big blue block. OK, and that base and apply ReLU on top of it. That gives you your document embedding. So that gives you the document embedding. OK, how is label embedding computed? Well, label embedding is also computed in a pretty similar manner. OK, so you take essentially Josquin, Desprez, Motet, and Chansons. So this must be some label name. So you take the label text, of course, ignore the stop words. So for so basically for getting the bag of words representation, they ignore the stop words. Get a bag of words representation, call it as ZL hat 0, right, or ZL hat not, right, and then basically pass it through an embedding block. This embedding block is also just similar to this embedding block in terms of architecture. But remember, the weights in ED are very different from EL. So EL and ED have the same architecture, but the weights trained are very different. OK, so that's that. So basically that gives you your label text embedding. Now these alphas and betas which are present in these, in this combination block. So alphas and betas are combination block parameters, and they are trained as part of the overall training for ED and EL. Now, of course, I've not talked about how they are trained, but they'll be trained as part of ED and EL. So now let's talk about how does Decaf really work? How is it trained, right? So module 1, module 2 on this slide, and module 3 and module 4 on the next slide. Again, if you've not looked at Deep XML video, you'll not understand what those modules are. So best look at the Deep XML video before looking at Decaf. OK, so let's see how does module 1 work. So in module 1, you jointly learn token embeddings E and also embedding modules ED and EL. Now remember, in these embedding modules ED and EL, they have their own Rs and they also have their own alphas and betas, right? So that's what you basically learn. OK, so how do you learn that is the question, and that is what I'm going to answer on the slide. So the way you do this is as follows. You basically take a label L and you compute the centroid for that label, or rather a representation for that label, by considering all of those data points which are relevant, for which the label is relevant, and then just doing a simple sum. OK, that basically gives you a centroid for that label. OK, and or rather a representation for that label. Now, given these representations for various labels, you're going to do clustering using the parabol tree. So essentially, you do the clustering just like in a parabol tree manner, balanced hierarchical binary clustering for 17 levels, finally leading to 2 raised to 17 different clusters. Okay. So now if you think about it, each of these clusters are more like meta labels. We can call them as meta labels. And the way you basically get the text associated with these meta labels is by combining the text ZL text associated with each of the labels that belong to any cluster. Okay. So if you have a cluster M, the overall text associated with the cluster M is basically a combination of the text associated with any of the labels in this cluster M. Okay. Now, that's one part. Now, of course, the next part is that if you look at a meta label node, it is relevant to a data point xi if it contains even one label that is relevant to the data label xi. Okay. With this setup in mind, what you do is to essentially solve this meta label, meta label XC problem, meta label extreme classification problem. Okay. So remember, the number of labels is 2 raised to 17 because that's your number of clusters. And you have already decided how to find the positive cluster versus negative clusters. So all you need to do is to now learn these one versus all meta classifiers H1 to HK, which basically help you sort of learn this XE problem. Okay. Now the meta classifiers H1 to HK follow this form. So essentially they are essentially you take the UM and you pass through the embedding matrix, and that's your HM. Now this HM is basically you're going to use this representation HM so as to essentially predict whether this particular cluster M is relevant or not for our data point. Okay. So that's basically that. So that's how essentially the surrogate task. Talking in terms of deep XML, the surrogate task here is essentially the classification to the cluster level, right? So extreme classification at the cluster level, and the representation, the feature representation is obtained using this balanced hierarchical binary clustering tree. Okay. Now, what do you do in module 2? In module 2, you need to come up with a shortlist. So essentially, in module 2, you are going to sort of come up with a shortlist and fine tune your ED, your EL, and your shortlister S. Okay. So remember, shortlist is basically nothing but a set of negative labels that can be associated with a single data point. Okay. So it also, of course, retrieves the label shortlist for all data points. Okay. So for each data point, the way you do this is basically start with each of those data points. And this time you also have trained the ED and EL, and therefore you have embedding E. This embedding E is actually used from module 1. It is learned from module 1. So that is how you obtain these revised cluster centroids now, okay, or cluster representations. Okay. So if you basically look at each label, the representation is going to be very similar to this one. It's just that rather than using xi, which is a syntactic representation, you basically have E times xi, which is basically a semantic representation in the embedding space E. Okay. Now, shortlister also uses k-means clustering the same way. Basically, it is done the hierarchical k-means, right? Hierarchical binary clustering, same thing, right? Exactly as it is. You're going to again map it as the same meta multi-label classification problem, but it is a new problem. Why? Because your clusters are no longer represented using just a combination of xi's, but represented using E times xi. Okay. Also, your HM is not as simple as just embedding, label embedding kind of transformation, but your HM actually involves your HM, the representation sort of involves combination. So in fact, the way the combination is done, the way the combination is done is as follows. You essentially compute UM1 hat, which is basically the same as the initial HM, which basically makes use of the embedding block L. Okay. So you make use of embedding block L for all of the label text that belong to this cluster M. Okay, so therefore you need to sum. You need to sum because the current cluster actually contains several labels, so you need to sum over all of them. Okay, so unlike in the first module where you actually summed up to get the embedding itself, here you're actually summing over the output of the embedding blocks. Okay, so that's the difference. So that's the UM1 part. So that's the UM1 part. Now you also have these alpha P's and beta P's. Now alpha P's and beta P's are essentially learned as part of the learning problem. Okay, so they're basically parameters to be learned, learnable parameters, and they're learned as part of them. So they are also of the same size D, right? So they are vectors of the size D, and they're actually learned as part of the learning problem. Okay. Now we are left with UM2. Now what is UM2? UM2 are meta-label specific refinement vectors. Okay, so to think of it, they're randomly initialized and they're trained as part of the overall learning problem. Okay, so remember there is a vector per cluster. Okay, so we have 2 raised to 17 clusters, and for each of those clusters is a label. For each of those clusters M, there is a label. Okay, so that's that. Now that basically gives you HM. Of course, you can connect this HM vector that you obtain to a neuron, which essentially decides whether this label is relevant or not. Okay. So overall, you solve this new meta multi-label classification problem, and on the way, you basically are learning the CP alphas and betas, and also you're learning your UM2 because that's basically learned, right? Of course, at the end of it, what you end up doing is to essentially learn the entire tree, using which you can actually do shortlisting. Okay, so the way you would do shortlisting is as follows. If you basically have any data point xi, you're essentially going to figure out top B clusters with highest, OVA scores HM. Okay, so you're going to basically take XI and you're going to use the beam search. So if you remember Parabel, you basically will remember beam search. You're essentially going to start from the root of the tree. You're going to sort of figure out the B leaf nodes with the highest, which are basically clusters in this case with the highest one versus all scores, and then for them you're essentially going to take all labels in those B clusters, because you see these clusters are clusters of labels after all. So you're going to take all the labels of those B clusters, and that's going to be your shortlist. Okay, that's going to be a shortlist. Now module 3 is pretty simple, and module 4 is simple as well, but let's go over them one by one. So module 3 is about initialization, right? So your ED and EL, their use is done. So basically you reinitialize them. Shortlister, yes, shortlister has to be frozen. So shortlister is the reason why you did module 2. Remember, why did you do module 1? To basically get the embedding matrix E. Why did you do module 2? To basically get the shortlister S. Okay. Now module 3, you basically get rid of ED and EL and reinitialize them. Shortlister is frozen. That's important. The combination block parameters alpha L and beta L are also reinitialized. OK, so and then finally, there are also refinement vectors for L labels that are initialized to E times ZL. OK, so we will see where are these combination vector, where are these refinement vectors used, but you initialize them to E times ZL, where what is E? This E is essentially from module 1. OK, so this is from module 1. And ZL is basically is a representation for every label. So that's how you basically initialize your refinement vectors. Now, what happens in module 4? Now, module 4 is, of course, the main training of Decaf, right? So you jointly learn L different one versus all classifiers, and these classifiers are going to be called W. And you're also going to learn a combination block. So in fact, let me actually start talking in terms of the picture that you see. Okay. You already know about this document text embedding, and you're going to do that. That's sort of obvious by now. So essentially, you take X, you multiply by E, that gives you X hat naught. And then you apply the ED, the embedding block, and then that gives you your text embedding, the document text embedding. Label text embedding, the way you do this in module 4 is basically, yes, you get get the bag of words representation, pass through the embedding block, you get a representation ZL hat 1. Now, you also want to make sure that you also have some learnable representations for Z. So that's basically ZL hat 2, which is what I mentioned, that you're going to initialize it using E times ZL, but you're going to update it as you train. So E times ZL is basically ZL2. Okay. Now, once that is done, essentially, yes, there is a combination block, and this combination block has the same architecture as the combination block we saw earlier. And that gives you basically gives you your weight vectors, your classifier vectors WM. Okay, so that's that. So you fine tune. So in module 4, what do? You essentially learn W. You learn the parameters of your CL, alphas and betas that are involved there, and you fine tune your ED, your EL, and your E using the shortlist S. Shortlist S you don't change. OK, so shortlister is not going to change. That module M2 is fixed. OK, but ED, EL, and E you're going to fine tune as part of your module 4. So for each of those matrices that are involved, the several matrices which are involved. So essentially each of those embedding blocks basically have this matrix R. Now, those R's, whether it is in ED or EL or several instantiations, they are all regularized using spectral regularization. You ensure that the spectral norm lies within a particular threshold. Okay. Everywhere, wherever you use logistic function, you basically, wherever you use the loss function, you use the logistic loss function. Okay. Lastly, basically, rather than learning just one model, you learn an ensemble of 3 different models, all of which share the module 1. Okay, so basically module 1, the embeddings E are shared by everyone, but otherwise, module 2, module 3, module 4 are trained individually. And then finally, you make the overall rank decision of the final labels using an ensemble of these 3. So how is inference done in Decaf? Well, the way the inference is done, when you get a new test document X, you essentially compute, you get a back of words representation for it, remove the stop words, essentially, get the embedding X hat. The way you do this is to pass through the embedding block D and apply relu on it. That gives you the embedding. Now you go to the shortlister model. Shortlister model, you do the beam search on the shortlister tree model, right? You get the B label clusters, and all the labels which belong to these B label clusters are essentially your potential candidates. Now, while you are doing this, you also get labels. So you also get scores from the shortlister, right? So shortlister also gives you scores using HM, right? So essentially, those scores are essentially similarity between your X hat that you obtained here and the HM one versus all classifiers that are present as part of the shortlister. Okay. So your overall label scores in Decaf are, however, a combination. As you see, the overall score for any label in Decaf is a combination of the shortlister score. So a shortlister score and also the OVA classifier score. So one versus all classifier score. So you're basically going to use you're going to get these one versus all classifier scores from module 4. Module 4 basically gave you those Ws. And you're going to apply sigmoid and you're going to apply sigmoid, multiply the 2, you get the label scores, which are the Decaf's label scores. Okay. Now, there have been so many different extreme classification methods so far. Some of them are tree based, some of them are, one versus all classifiers. Some of them are essentially deep learning based methods and so on. STAC is the only other method using the deep XML pipeline. Attention XML is another deep learning kind of method. What you observe across these 2 data sets on precision and PSP is that Decaf essentially can be 2 to 6% more accurate. Of course, it's more accurate than any other method, but it can be more accurate, 2 to 6% more accurate, as well as an order of magnitude faster compared to many other methods. So here, essentially, you observe that it is 0.1 milliseconds for GPU and 1.15 milliseconds for CPU. Okay. So Decaf could be up to 3% more accurate than STAC, the algorithm that I talked in the previous video. Okay. So if you look at the quantile-wise plots, okay, so these are special kinds of plots. Let me discuss the x-axis, y-axis. But what you observe is that this also compares across different methods, and you see Decaf winning across, right? So this is on 2 different data sets, LF Amazon titles 131K and LF WikiC also titles 320K. What you observe is there's a complete thing. So there's a complete data set results where you see Decaf winning, but you also see results for 5 different quantiles. Now these 5 quantiles have been created by dividing the label set into 5 different buckets. OK, so this first bucket basically contains 4,000 labels. OK, so this one contains 11,000 labels, this one 18,000 labels, and so on. This one 68,000 labels. OK, so these labels are first sorted by their frequencies, and then you do a equal number of data points per bin. So and you get like 5 bins. OK, so therefore this bin basically contains head labels. So why head labels? Because just 4,000 labels are, the number of data points covered by 4,000 labels are equivalent to the number of data points covered by the 68,000 labels and the tail. So therefore, the way to read this plot is that this part is tail and this part is basically head from a label perspective. Okay, so that's that. Now, what do you observe from these plots? You observe that Decaf really wins in the tail. OK, so doing extreme classification for tail labels is actually very difficult. Why? Well, because tail labels do not have enough data points. That's why they're called as tail labels to train. Not enough data points to train. Of course, you expect your accuracy to be poor, but Decaf actually wins over those methods in the tail, which is really good. OK, So here also you see Decaf actually wins over the tail, although on the head it performs almost equivalent to several other methods. So doing good on head is easy, but doing good on tail is difficult, which is where Decaf is good at. Okay. Now, unlike STAC, which I discussed previously, Decaf uses parabol shortlist. So remember the shortlister, the M2 module 2 that I talked about was a parabol, k-means binary hierarchical tree, right? So STAC basically used approximate nearest neighbor search based shortlisting, right? So using HNSW, HNSW is a approximate nearest neighbor search method. It actually stands for hierarchical navigable small world. Okay, so unlike HNSW, Decaf actually uses parabol. And what people have observed is that Decaf with the parabol is, or rather, yeah, I mean, essentially, Decaf by itself. So of course, it doesn't exactly use parabol, but what it uses is this parabol-like shortlisting, right? I mean, it basically creates that tree and then does shortlisting. So what is observed is that Decaf's shortlisting is way better than any other shortlisting. So Decaf shortlisting really gives you much better results. Now, Decaf used label metadata. Remember in STAC, we never said that, hey, we'll come up with a label embedding. Why? Well, right? I mean, a separate label embedding rather than actually just using a combination of text, which is represented by data points for which the label is relevant, right? So Decaf basically leveraged label embedding. Now you could do the same thing with other methods as well. So you could do parabol and parabol plus label embedding, bonsai plus label embedding, and dismac plus label embedding. Okay. So this metadata is basically the label embedding that I'm talking about. Okay. So, but now what is observed is that even if you basically add the metadata or the label embedding to these different possible methods, you still observe that Decaf gives you the best result. So even if you give metadata to these algorithms, Decaf basically knows how to best use it. So in summary, in this video, I talked about the impact of incorporating label metadata in the form of labeled text. We do see that there's a positive impact everywhere. So across algorithms, using labels actually gives you better results, right? But Decaf gives you the best results. Decaf is a deep XML algorithm, right? It's a deep learning based extreme classification algorithm. It is 2 to 6% more accurate, as well as an order of magnitude faster compared to state of the art deep, extreme classification methods. Okay. So if you want to try out code, the code is right there. Okay, so that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.